All right, let's talk about building systems from massive scale. Ever really stop to think about how global platforms handle a constant fire hose of data? Millions of messages every single second? Today, we're going to do a proper architectural deconstruction. We're going to tear down a publish-subscribe system and trace its evolution from a pretty simple idea to a truly enterprise-grade powerhouse. Let's jump in. So, here's our game plan. We'll start with the basics, the what and why of PubSub. Then we'll analyze a first attempt at a design and see exactly where it falls apart. After that, we dive into the much better broker-based solution, digging into its engine, how it handles failure, and we'll wrap it all up with the big architectural takeaways. Okay, first things first. Before we get lost in the weeds of partitions and brokers, let's establish the core problem. What is the fundamental challenge in distributed systems that the entire PubSub pattern was invented to solve?
At its heart, PubSub is all about asynchronous communication. Think of it as a broadcast system for your services. You have producers, or publishers, that send out messages to a named topic without having any idea who, if anyone, is listening. And then you have consumers, or subscribers, that tune into that topic to receive the messages without ever needing to know who sent them.
And right here, this is the entire reason for its existence. The magic word is decoupling. By putting that topic in the middle, your producers and consumers are completely independent. You can spin up 1,000 new consumers, and the producer side doesn't even notice. You can change how a producer generates data, and as long as the message format is the same, the consumers don't care. This freedom is absolutely essential for building complex microservice architectures that can actually scale.
So, let's imagine we're building this from scratch. It's totally natural to start with the most straightforward approach you can think of. So let's architect that first simple version, and then really put it under the microscope to find its breaking points. Okay, so this first design seems logical, right? A producer writes its message to a central queue for a given topic. Then, a component we'll call the message director wakes up. Its job is to look in a database to see who's subscribed to that topic. And then, and this is the critical part, it copies that one message into a separate, dedicated queue for every single subscriber.
Now, for a handful of users and a few topics, this probably works fine. But we're talking enterprise scale. So where does this architecture start to creak and groan? What happens when you have thousands of topics and millions of subscribers? Where are the I/O bottlenecks just waiting to happen?
And here are the two killers. First, you get what we call a combinatorial explosion of queues. And second, you're creating a tidal wave of duplicated data. These two problems are not subtle. They will bring the system to its knees.
This quote from the systems designers just nails it. The math is brutal. If you have, say, a few thousand popular topics, and each one has 1 million subscribers, well, you're looking at managing potentially billions of individual queues. From an operational standpoint, that's just an absolute nightmare. It's completely unsustainable.
Okay, so that first design is a dead end. Let's pivot to a much more sophisticated architecture that's built from the ground up to solve these problems. This new design introduces a central nervous system for the whole operation, the broker.
So in this model, you have a cluster of these broker servers. They are the heart of the system. They receive and store all the messages. To keep things running, a cluster manager keeps an eye on the broker's health and handles data replication. A consumer manager deals with things like authentication and access. The whole philosophy has shifted from copying data everywhere to managing it centrally and efficiently.
And here's the solution in a nutshell. We have completely gotten rid of the one queue per consumer idea. It's gone. Now the message is stored once inside the broker cluster. Consumers just connect and read from there. This one change instantly solves both the queue explosion problem and the massive data duplication problem.
So that's great, but it raises a new question, right? How do we stop the broker itself from becoming one giant bottleneck? The answer is some really clever internal engineering designed specifically to parallelize work and achieve insane I/O throughput.
So the first key concept is that topics aren't single giant things. They're actually broken up into smaller pieces called partitions. You can think of each partition as its own independent ordered log. By doing this, you can spread the partitions for a single high-traffic topic across many different machines. This lets you parallelize the reads and writes, which is how you scale throughput horizontally.
Now this is where the design gets really elegant. Inside each partition, messages are written to disk as immutable records. They're just appended to a file, kind of like a database commit log. And every single message gets a unique sequential number called an offset. This offset is incredibly powerful.
It means a consumer can connect and just say, hey, give me all messages starting from offset 1 million. Another consumer can be reading from offset 5 million. They can read at their own pace from the same data without ever interfering with each other. It's a lock-free design, and that's absolutely crucial for high-speed reads.
So how does the system make sure one partition doesn't get all the traffic? Well, when a producer sends a message, it doesn't just go to a random partition. The system uses a smart, weighted round-robin algorithm. It distributes the new messages evenly across all the available partitions for that topic. This balancing act is key to preventing hotspots and ensuring smooth, predictable performance. So we've got performance, we've got scalability, but what about reliability? What happens when a server holding a partition just dies? This is where the system's fault tolerance model, based on replication, really shines. For every single partition in the cluster, the system uses what's called a leader-follower model. One broker is elected the leader. It's the only one allowed to handle writes for that partition. At the same time, other gropers act as followers, and their only job is to constantly make an exact copy of the leader's data. If that leader broker ever goes down, the cluster manager notices immediately and promotes one of the perfectly synchronized followers to become the new leader. The failover is fast, and you lose zero data.
And this system is not messing around when it comes to durability. The magic number here is 3. For every single partition, the system insists on maintaining 3 full copies or replicas of the data, and it's smart enough to place each of those replicas on a different physical broker. This isn't just basic backup, it's a hardcore commitment to high availability. It means you can lose a server, and the system just keeps on running without missing a beat.
All right, let's pull back up to the 30,000-foot view. What are the big engineering lessons we've learned by comparing these two radically different architectures?
Well, when you put them side by side, it's not even a contest. The first design crashes and burns on scalability with its massive queue complexity and is incredibly wasteful with storage. Meanwhile, the broker model scales beautifully with partitions. It's super efficient with data. It has fault tolerance baked right into its core with leader-follower replication, and, most importantly, it preserves that beautiful decoupling that we wanted from the very beginning.
You know, this broker-based architecture is a beast. It's proven, it's robust, and it powers some of the biggest data platforms on the planet. But it does leave us with a pretty tantalizing thought. This design solves for today's scale, but what about tomorrow's? What happens when the requirement isn't millions of messages, but 1 trillion per hour? What's the next architectural leap we'll need to make? That is the next great engineering challenge.